All right, welcome everyone to lecture 16 of Intro to Space Navigation, Spring 2025 edition. Welcome back from spring break. I want to go through and introduce after I share my. Okay, there we are. We should be back. So remember our course map. So I've tried to time it so that when we get back from spring break, we start a new unit, and we're getting into the stuff that I really like. So we've largely been building a foundation for the first chunk of the class. In my opinion, and I'm openly biased, I'm an image-based spacecraft navigation person. We're getting into the fun stuff today. And today we're going to start a 4-lecture long unit on star trackers, where we're going to talk about how to use a camera bolted to the side of your spacecraft to estimate your orientation or your attitude in 3D space. And so that's going to be what we talk about today, and for lectures 17, 18, and 19 as well. And then we'll go into a 3 or 4 lecture series on Kalman filters, which is sequential estimation applied to kind of incoming measurements of a spacecraft state. And then our last lecture will be more general optical navigation. So full moon photos and full Earth photos to get your position, or we might get into some more exotic stuff like crater-based navigation or visual odometry. There's some fun stuff to look forward to at the end of the class. But yeah, Star Trackers, one of my favorite units. Today's one of my favorite lectures. I think we're going to have a lot of fun. So let me start by and so this is going to be kind of an open question, like go ahead and turn your mics on if anybody has any thoughts. But let's presume for a moment that you are stuck in space. You're floating in the vacuum of space. Maybe you're lucky enough to be in a spacecraft, so you're not just in your EVA suit. You realize that you're lost, and you want to get unlost in space. Start from nothing. What do you want to do? What sorts of measurements do you take? How do you reestablish your position and velocity and orientation in space?
I feel like the first, go ahead.
Oh no, you can go.
I feel like the first obvious thing I'd need to do is like try to stabilize myself. So make sure that I have like one solid field of view and I'm not just.
Yeah, that's a good thing. Stop rotating. That's a good idea. Get your state to something stable. Good. But then in that case, well, actually, no, that's a good point. You would need to be able to estimate your rotation in order to stop rotating. And we've already learned how to do that. What's the instrument to estimate your rotation? That's a tricky one. I realize it's been a week. That's an IMU. It's an
Gyroscope?
inertial.
I'm
Yeah, so you can use an inertial measurement unit, which will determine your rotation with respect to inertial space. You can basically just fire your thrusters until this thing reads all zeros, and then you've at least stopped spinning. So that's a solid start. So then what would we do? Now we've stopped spinning. How do we continue to claw our way out of this hole?
You'd look around for like something to like an anchor point or like a reference point to try and figure out
Sure.
where you are, like a planet or a star.
Yeah, absolutely. Let's assume for the moment that we're somewhere in the Earth's sphere of influence. So you should be able to see the Earth. Okay, so then you should actually know generally. Now maybe not. Maybe you're completely stuck and you have no idea which way to look. If you have even a rough idea of where the Earth is with respect to you, you could point in that general direction and see if you can see it. You can either point a camera at the Earth, you can point an antenna at the Earth, that sort of thing. But before you can even start to point anything anywhere, you have another problem, which is which way am I pointing right now? Right? Determining your orientation, and this is the main point I want to get across right now. Determining your orientation has to come before determining your position, right? Because your sensors that you use to determine position and velocity generally need to be oriented a specific way. You need your camera pointed at the Earth, you need your radio system pointed at the Earth, what have you, your high gain antenna. Orientation comes first. So that's kind of my point here to motivate this. So attitude determination must come first. So today's lecture, by the way, is on space cameras. And my point is that attitude, determination must come first. Okay. So there are several attitude instruments. To determine the pointing of your spacecraft, but star trackers are the gold standard. And a star tracker is little more than a camera that is specifically designed to point at stars and then tell you which way you're facing, which might seem rather arcane, but we're going to get to the bottom of that over the course of the next several lectures. So how does a star tracker work? So let me divide the screen up into 4 segments here. So what I'm contending is that if you have an image that is almost all black except for some lit pixels, which are stars, then you can determine the orientation of the spacecraft reference frame with respect to some inertial reference frame, like the International Celestial Reference Frame. And that you can do that in 4 steps. And not only can you do that, but you will do this because this is homework 4. So for homework 4, I'm going to give you a starfield image and some camera parameters, and then you're off to the races. And then you need to tell me the orientation of the spacecraft with no other information. Homework 4 is probably my favorite one. I love how open-ended it is. But you will be able to say that you coded up a star tracker from scratch, which is more than a lot of people could say. So that's something to look forward to. So how the heck do we even do this? Let's start from the camera itself. So a star tracker consists of a space camera, which is today's lecture. So you can think of this is lecture 17, or sorry, 16. And if you have a camera that is pointed at stars, say there's 3 stars, and you take an image, then we know that there will be stars in the image, like so. In front. So the idea is that this camera tells us about we go from an image, starfield image, which is pixels, to line of sight directions in the camera reference frame. So imagine that the camera has some sort of X direction, some Y direction, and then some Z direction, right? Okay. So what we're finding is line of sight directions in camera frame. That's what we're doing today. Now, this only helps us if we have a star map. You might say, in order to determine our orientation from a starfield image, don't we need to know where all the stars are? And the answer is, yeah, kind of. You need to know where most of them are. So we need a star map, which is lecture 17. We'll talk about that next time. And so a star map will tell you things like, and here's my best Earth. You've got some little continents, Antarctica, and let's see here. How's the best way to draw this? There we go. And let's say that you've got some Earth X direction, some Earth Y direction, some Earth Z direction, and then that you've got a bunch of stars, which we're going to treat as being at infinite distance away from the Earth. Right? Let's just look at this particular star right here. Well, it's going to have some azimuth angle, and it's going to have some elevation angle. So a decent start to your star map is going to be a list of azimuth and elevation angles for every single star in some international celestial reference frame. So this star map is going to basically be list of star directions in inertial frame. Okay, that still doesn't quite help us, right? The most difficult question is star ID, which is an index search problem. This is the hardest part. This will be lecture 18. And that is, okay, just because I have a map of all the stars doesn't mean I know which stars these are. So you need to be able to somehow look up these stars in a reference table before you know which way you're facing. Because if you know which way you're facing, you can just go, okay, I know which way I am. I know the relationship between the camera frame and the inertial frame. I know the star vectors in the camera frame. Let me just put those in the inertial frame and then find the nearest match in the catalog. Boom, you're done. That's backwards because we don't know the camera to inertial relationship. That's the whole point. So you somehow need to be able to look up a star and determine which one it is before you know which way you're facing. And that is tricky. So we're going to talk about that. And that amounts to an index search problem. And this diagram is going to make a little bit more sense later. But imagine you've got essentially a numerical descriptor for every set of stars. And you are going to be searching in an index for something with a similar descriptor. So I'm going to say compare asterism descriptors. An asterism is just a group of stars. To identify stars. Now let's say that if you know, okay, these 3 stars in my camera are some set of 3 stars in real life. Now you've got the same unit vectors expressed in 2 different reference frames. Then what you're left with is something called Waba's problem, which is lecture 19. And Waba's problem is basically saying this. Well, if I've got my camera and I know it's pointed at these 3 stars, I know those stars in my camera frame, I know those stars in the inertial frame. What is the relationship between this camera frame and the inertial frame? So the way I draw that is with a couple of like rotation arrows. Basically, find the transformation between frames. So today is going to be camera models and image processing. Next class is going to be how do we keep track of where all the stars are. Next class is going to be how do we set up a database and search for our stars. And then finally, it's going to be how do we solve and find the orientation of the camera. And that'll be about it. So today, questions on that before we move on? Okay, cool. Today we will focus on space cameras as navigation instruments. Okay. So what goes into a camera? Let me draw a picture of a camera. I guess this can just be a rectangle. Nope. Go. And then something like this. So out here, you've got a star field. And this is going to be the field of view of the camera, which I'm going to write as FOV. So it's going to be an angle. And what you have right here is a light baffle. So not all cameras have this. Your phone camera won't have a light baffle. This is not the same thing as the lens assembly. So if you've seen, professional photographers with those massive lenses on the camera, that's not this. This is something that is on a space camera, and terrestrial cameras you don't generally see have a light baffle. A baffle is a lot like a gun silencer, or I use the metaphor of like blinders on a racehorse. Essentially, this is here to stop stray light. Let's say maybe the sun is down here, right? And we don't want the sun to kind of glint on the edge of one of the lens elements and then have some sort of internal reflection business going on, and then you get stray light. We don't want that. So your light baffle keeps out stray light. Then the light comes into the optical assembly or the lens assembly. And I'm going to draw this as just having a bunch of little lenses. So optical assembly. And so the lens focuses the light onto, back here, some sort of grid, and that grid will read off, this is the focal plane array. So pixels in an image are actual physical things in a camera. So they're generally wells that are filled up with voltage corresponding to the number of photons that make it into the image. And so if you get more photons falling into that particular well, then that picture element or pixel is then brighter. It's going to be a larger value when you're done processing your image. So the focal plane array is a whole bunch of buckets which collect photons. Almost imagine like rainwater collecting a bunch of buckets. And then each of those buckets is read out into a computer, a data processing unit. And when you're done, you have an image, which is really just a matrix. It's a matrix of numbers. So the value of each element in the matrix is the brightness of that image, of that particular pixel in the image. So let's go through and write this out. A conventional space camera consists of a light baffle, which blocks stray light, an optical assembly or a lens assembly, so this is a series of refractive lenses which focus the light. Sorry, I guess focuses would be proper English. All right. Next is a focal plane array. Which converts photon counts into electric potential. And then finally, we've got the unit. Which converts voltages at wells. I'm just gonna say voltages, sorry. So keep it simple. Converts voltages to digital numbers. And then an image is a matrix of brightness values at each picture element, which is a pixel. Often stored as 8-bit numbers. So generally, your brightness is going to be between 0 to 255. But not always. You'll get 12-bit depth sensors, you'll get 16-bit depth sensors. Just gives you more granularity. But generally, the cameras that I've worked with are 8-bit depth. Right? So what this describes is a bunch of hardware that basically takes you from reality to brightnesses at individual pixels. So let's talk about how an individual star becomes a bright spot on an image, which we don't really care about. What we want to do is be able to go the other way, to be able to go, okay, I have a bright spot in my image, tell me where the star is. But you got to do one way before you can do the other way. So questions about this? So far, so good? All right. So we're going to start with something called the pinhole camera model. A real camera contains multiple lenses. But it is often useful to model the camera as though its lens assembly had shrunk to a single point. Or a pinhole. So what if instead of all these fancy lenses, we just say, okay, my entire camera is a box with a pinhole in one side. The light comes in, all the light rays, none of them bend. They are all perfectly straight lines, and they all land somewhere on the focal plane array. And this is not a bad first order approximation of a camera. This will get us pretty far, actually. The location of the fictitious pinhole is the focal point. The distance from focal point to the focal plane array is the focal length. Or F. An image taken this way will be upside down and backwards. And it must be rectified. So I can draw a picture to make that a little bit more clear. So imagine you've got a camera aperture. We're going to start with a focal point right here. Okay. And I'm going to say that you've got some focal plane back here. I can clean up that last line a little bit. Yeah, that'll do. And then from the center of the focal plane, draw a straight line out, make that a little bigger, and then continue the straight line out. And let's say that this intersects right here. Bear with me. You might be saying, why are there two images? Just bear with me for now. And this is going to head all the way out. All right. Now, let's say that there's some point out in space, which looks like this star. So you know what? I'm going to color code this. Let's have some fun today. I'm going to make this like a blue. Okay. Okay. So let's say that there's this point out in space. And if you were to draw a straight line from the focal point to this star, it would intersect an image plane right here. And it would also come through let's see, am I doing this wrong? Yeah, there we go. They intersect upside down and backwards. So your real star, I tried to kind of get the points of it correct here. The real star is going to be upside down and backwards by the time you get to the focal plane array. So this is the focal plane, which means that if this is the focal point, then this distance must be f, the focal length. Okay. So then the issue is, I don't really want to work with an image that's upside down and backwards, right? I'd much rather work with an image that's up, right side up. So I'm going to pretend that there's also a plane right here called the image plane, which, to be clear, doesn't exist. If you open up a camera and you look for the image plane, you won't find it. If you open up a camera and you look for the focal plane, you will find it. There's actually a series of pixels, like voltage wells, that will collect the brightness, the photons as they come in through the camera. But there's nothing there at the image plane. We're going to pretend that at a distance of 1 in front of the camera, there is this fictitious image plane. This direction here, the forwards direction, is referred to as the bore sight. And so if you have some point in 3D space, and let's go through, let's also define the camera frame. The camera frame has X pointing to the right, Y pointing down, and then Z pointing out along the camera bore sight. And this point out here in 3D space is going to be XI, YI, ZI. Okay. And then I'm going to try to find some room for it here, but this point right here is going to be little xi, little yi, and 1. Clearly in the camera frame, the projection of something in 3D space onto a point that is 1 away from the focal point along the z direction must have a z element of 1. So you're just taking that and scaling it. And then this other point over here is going to have x, f, y, f, and then negative focal length. Right? So now we've got the same point described 3 different ways. While we're at it, I'm going to introduce one more reference frame. I know this is a lot. There's also the pixel reference frame, which I'm going to try to draw a little bit better. And we'll spend some more time on that later. But there's a picture, this is the pixel reference frame. So you can describe the location of a point in an image in pixels. You can describe it in the camera reference frame, which is the only reference frame we're working with right now. You could describe it as a point on the image plane, a point on the focal plane, or a point out in 3D space. So this is the, let's be clear, this is the camera reference frame. So let's start with that. This has Z is forward along bore sight. X is to the right. And Y is down. We introduce the fictitious image plane at unity distance from the focal point. So I would much rather work in image plane coordinates than focal plane coordinates because I'm going to get really confused by the upside down and back. All right, so now here is a neat observation. This is a good place to start. A point in 3D space, which I'm going to write as big xi, big yi, big zi. Oh, strictly speaking, hang on. I skipped something. This should be xfi, yfi. There we go. So in this case, I is just the ith point floating out in space. So this is star I, that sort of thing. This is a point in 3D space, which has x, y, z coordinates. There is also this vector x, fi, y, fi, and then negative focal length, which is this point here. And then there's also, so this is a focal plane point. There's also a point on the image plane, which is x, I, y, I. And the observation is that these are all similar. It's my best similar icon. So it's the same line. I guess my handwriting leaves something to be desired, but this star that's upside down and backwards, the star on the image plane, and the star that's floating out in 3D space, it's all the same perfectly straight line according to the pinhole camera model. And so that means that you can take something that's floating out in 3D space, and if you scale it by its component, you'll get a image plane point. So xi is equal to big xi over big zi, and yi is big yi over big zi. And that should make sense. If you take a point in 3D space that's already in your camera frame, and you scale it to have a z component of 1, you are now on the image plane. Okay, great. Why do we care about that? Well, there's more steps, but that is our first step, is to go from a 3D point to an image plane point. Okay. So how do we proceed? How do we go from a point on the image plane to a point, or let's say to pixel coordinates in an image? All right, well, that is that pixel reference frame that I kind of hinted at before, the one in purple, right? So we will define pixel frame as being centered at the middle of the top left pixel. Okay. And we'll say that U is to the right, or basically just increasing columns. So as you move from one column to the next, you are going along the U direction, and then V down, or increasing rows. Okay. And there's also something called the principal point. Principal point. The principal point, which is U principal V principal, is the intersection of the z-axis with the image plane. So to clarify, the principal point is that right there. It's the intersection of the bore sight or the z-axis with the image plane. And you might say, is that not the middle of the image? And it's like, actually, no. Wouldn't that be easy? The true middle of the image is generally not the direction that you are looking through the camera bore sight, just because of, mistakes in manufacturing, are your lenses truly orthogonal to your focal plane, that sort of thing. You're generally pretty close. If your principal point, which is also the center of your distortion, which we'll talk about that later. If your principal point is not close to the center of your image, something has gone wrong. You need to go talk to your camera manufacturer. So let me draw this here. So let's say we've got an image, looks like so. Okay, and this is our top left pixel. Then we have some U vector going this way. The vector is going this way. And then you've also got some point here, the middle of the image, which is U, P, and V, P. And this is the principal point. Where as drawn, Z is into the page. So this is Z is into the page. Okay. That still doesn't help us. Right, we're still not quite done. As a matter of fact, you know what? I'm going to be cheeky here. Sorry, this is going to be annoying for everybody. I'm going to move where it says principal point. Scoot that up to like maybe over here. Scoot this too. Sorry, I know I'm cheating. You can't do this on your handwritten notes. I just want to get the point across that this is the X direction and this is the Y direction. Right? Okay, so maybe you can see that we're kind of getting somewhere. So imagine there's a point on the image which you could express as xi or yi, but I'd really rather express it as a ui or vi. Let's see. So we need a few other things. We're still not quite done yet. The distance from pixel center to pixel center is called pixel pitch. Generally tiny, on the order of microns. And that's going to have an X direction and a Y direction. So mu X and mu Y. So X would be the width of a pixel and Y would be the height of a pixel. Okay? Mu X and mu Y are generally similar. So generally, pixels are roughly square. So if your pixel pitch and the X and the Y direction are substantially different, something has gone wrong with your camera manufacturer. So when calibrating a camera, we don't know the pixel pitch or the focal length. But rather we know the ratio of the two. So I'm going to introduce dx, which is focal length divided by pixel pitch in the x direction, and then dy is focal length divided by pixel pitch in the y direction. So roughly speaking, dx and dy should be very similar because f equals f and mu x roughly equals mu y. So dx and dy should be very similar. And dx and dy is the focal length expressed in pixels. So you're scaling your focal length by the width of your pixels. You don't get to know either one, but this is plenty. So you could say, oh, my sensor is 6,000 pixels away from my focal point. And I don't know the length of a pixel. It's kind of one of those similar triangles problems. You don't have the absolute scale, but this is enough to actually get us most of the way to our answer. So these can be thought of as focal length in pixels. All right. So here it comes. We're almost there. The relationship between an image plane point and a point in pixel coordinates is, here it comes. The u direction is just the scaled x direction with another term, which we'll talk about in a second, plus our principal point. And our v direction is our scaled y direction plus principal point. So what's happening here? We've got a scaling, you've got some shear, and you've got a translation. So to go from x and y to u and v, you do need to account for the fact that your camera generally is not going to be a perfect rectangle. It's going to have a little bit of parallelogram business going on. So that's why we have this alpha term, which accounts for shear. Alpha is generally pretty small. Some camera models just treat it as 0. If your alpha is substantially large, you need to go back and talk to your camera manufacturer. But hopefully you can see we're basically just scaling from real world distance into pixel distance and then translating by our principal point. And then that gives us our coordinates in pixels. So to be clear, and we're almost at a good checkpoint here, this can more compactly be written in homogeneous coordinates. Some of you that have taken robotics might be familiar with the homogeneous matrix, which gives you a rotation and a translation. This is actually a similar construct. If that doesn't sound familiar, then ignore it. Forget I didn't say anything. U, V, and 1. All we're doing is taking these equations and popping them into a matrix. This becomes dx alpha up 0 dy vp 0, 0, 1. And then this is x, I, y, I, and 1. And this matrix here is K. So now we've got a point in the image plane, and by multiplying that point by K, this matrix that we can build, we get UI, VI, 1. So now we've been able to map from image plane points to pixel points, where the matrix K is the camera calibration matrix. Also known as the intrinsic matrix. And the ensemble of characters, dx, dy, alpha, up, and vp, are intrinsic camera parameters. There are also extrinsic parameters, which is basically pose, the rotation and translation of the camera. So those are things that can change. And distortion parameters. So the extrinsic parameters is basically what we're trying to estimate at the end of our star tracker unit, our camera attitude. Distortion is what we'll talk about next. So one thing at a time. Maybe that'll be after our 5-minute break. A camera whose intrinsic and distortion parameters are known is said to be calibrated. And camera calibration is its own topic. It really deserves its own lecture. I'm going to talk about it very briefly at the end of today. But basically, if you don't know DX, DY, alpha, UP, VP, how can you find those for a camera that you just purchased? That actually would be a great project. We could talk about projects at the end of the class too, but one thing at a time. Now, in practice, well, I'll talk a little bit about camera. We'll do one bullet about camera calibration. Camera calibration is typically done on the ground and redone in flight to update parameters. So that's what was done on Artemis 1, for example. We'd calibrate the camera on the ground, and then the flight software would have the calibration parameters, but then you might say, well, there might have been some thermal shift in the camera, better recalibrate, and then we'll use the results of the last calibration to update the next calibration. Now, in practice, we often want to convert from pixels to image plane points. So we want to work this problem backwards. And we can do that analytically, actually. We can say, okay, x, I, y, I, 1 is k inverse u, I, v, I, 1. And you could just do inverse of k in MATLAB or Python, that's fine. Or you could do an analytical inverse, which would look like this. 1 over dx negative alpha over dx dy. Vp alpha minus up dy over dx dy. 0, 1 over dy, negative vp over dy, 0, 0, 1. And that's what multiplies ui vi 1. Okay, now here's the cool part. This vector right here, this xi yi 1, It's actually impossible, if you scroll up to the original diagram here, it's impossible to get the distance that we've lost, right? Which also with stars, distance doesn't really mean anything. For all practical purposes, stars that we use for navigation are infinitely far away. Right? Now, really, we know some stars are further away than others, and there's parallax, and that's fine. For today's star tracker discussion, stars are at infinite distance. So we don't really care about its x, y, z. We just care more about. But you can see that that unit vector would also be proportional to or be similar to this x, y, 1. So if you scale it, if you normalize this, you can get E I hat cam, which is a unit vector in the camera frame. Which is our goal for today. Remember, our goal is to go from pixels in an image to line of sight directions in the camera frame. Unfortunately, we have plenty more to discuss because the devil's in the details. We didn't talk about noise or aberration or a bunch of other stuff. So why don't we take a 5-minute break? So it's 7:04 for you. Let's come back. Let's call it break turn at 7:10. There we go. And then we will talk about the rest of our image processing for now. All right, time to start back up. So I'm looking ahead at my notes. I think we probably have too much to get through today, so I might let part of today's camera discussion bleed over into next lecture. But let's get as far as we can. So I've discussed how we can go from pixel coordinates to points in a camera frame using this inverse camera calibration matrix or inverse camera intrinsic matrix. But we didn't talk about noise. We didn't talk about aberration. We didn't talk about lens distortion. We didn't talk about the actual image processing to get the star centroid values. There's a lot of other stuff to talk about before we're ready to kind of take this step. But this is kind of, we can see the end of the journey here. Let's talk about some of the other things that we can't ignore. So, image noise. So the effect of noise is to perturb a pixel's digital value. So that's all noise is. For a given pixel, we're going to make it a little too bright or a little too dim because of, well, because of a couple of different things. The first is readout noise. So this would be generated from converting electric charges to digital numbers. And so then you could think of this as analog to digital conversion noise. Which comes from quantization of a continuous signal. So one example would be, let's say that the true value at a pixel is 5/8 or 0.625. Okay. If a fully on pixel for an 8-bit depth image is 255, then the closest we can get is 159 out of 255, which equals 0.6235. So there is no 5/8 full for an 8-bit depth image. There's 159 255ths, which is as close as we can get. But you can see how we've just introduced 0.00, what is that, 15, elements of error, but there is now some error. So this is as close as we can get. With a bit depth of 8. Okay, the next is dark current. So even an image with the lens cap on isn't completely black. So the way we handle that is capture a dark frame. So what you can do is, let's just take a lens cap on image and then subtract that pixel value from every pixel coming out of future images. And that'll get rid of some of the noise that goes on that just comes from the camera itself. So capture a dark frame, remove from future images. All right. Next is photon shot noise. Which is noise associated with generation and collection of photoelectrons at the focal plane array. Right. Next is fixed pattern noise. Which is caused by idiosyncrasies in detector sensitivity. Not every pixel is going to be the same sensitivity as every other pixel. There is reset noise. So it is impossible to purge all charge, or say all charges, in the focal plane array between images. There's always going to be some leftover voltage after you're done reading your image. And then there's radiation effects. And this is the last one for now. So this can cause stuck pixels. So always 1 or 0. Bit flips, etc. Radiation can do all sorts of fun stuff to your camera. Actually, if you look at the cameras on the International Space Station, you'll see that they have clear radiation damage, and they've got stuck on pixels just from being out in low Earth orbit for that long. So not that much we can do about image noise, except for this dark frame business I talked about. The next I want to talk about is optical aberration. Optical aberration. Okay. And this comes in 5 kind of flavors. So there's spherical aberration, which blurs point sources of light. There is chromatic aberration, sometimes called coma, which essentially point sources of light near the image edge smear into a streak. There's astigmatism, where blur is greater along one axis than another. There is curvature of field, which essentially, because you have an incoming light wavefront, which is spherical in nature, projecting onto a flat plane, you can either have the center of the image in focus and the edges slightly blurry, or you can have the edges of the image in focus and the center slightly blurry. You can never have, or I'll just say it's impossible, for the entire field of view to be in focus. And then there is finally lens distortion, which we can separate into two types: radial distortion and tangential distortion. Now here's the thing. Lens distortion actually moves points around in an image. This is unacceptable. We must account for this. So a lot of these other noise and aberration sources are a bummer, but if you have a blurry star that is now a slightly more blurry star because of spherical aberration, okay, big deal. If your image is warped such that stars physically move across the field of view from where they should be, that's completely not okay for a star tracker. We have to have a rock solid understanding of our camera's distortion. So allow me to do a quick diagram here, and this is going to be, well, you know what, we're going to do our best. This is, imagine you start with an image which is truly rectilinear, like so. That's meant to be a true rectangle. And then imagine you've got that original image again. We'll do it another time. Right. If your points are all warped inwards, it's going to create this kind of barrel shape. Okay. Where along the center, it's actually going to look about the same. But then you get this kind of shape. Or if every single point is stretched outwards, you get this kind of pincushion shape. Where, again, along these main axes, it's going to look about the same, but then you'll get kind of this effect. Okay. This is called barrel distortion. This is called pincushion distortion. Okay. And generally, we will model, so this is radial distortion. With three numbers, K1, K2, K3. Now there's also tangential distortion. So I'm going to cheat for a second and just pop this guy down here. And say, okay, well, there's another type of distortion which is caused by not mounting your lens assembly perfectly orthogonally to your focal plane array, which not only means that your camera isn't quite looking in the right direction, but it also changes the projection. The best way you could think about tangential distortion is, imagine you're setting up a projector and your projector is skew. It's not pointing like perfectly at the whiteboard or the blackboard or whatever your projection surface is. And so you end up with something that kind of looks like this. Kind of goes out like here. Where along this axis, it looks about the same. But basically, it's blown out on one side. Too small on one side, too big on the other. Or you could think of it as being rotated the other way. So you've got like yay. Here we go. There we go. So you can have vertical or horizontal, or generally both. Generally, you'll have some vertical and some horizontal tangential distortion. Now, obviously, these are extreme, right? If your images look anything like any of these, something has gone seriously wrong. But these are kind of caricatures that we're using to describe these types of distortion. Every camera is going to have some radial distortion and some tangential distortion. And I'm going to introduce 5 more camera parameters. So remember dx, dy, alpha, up, vp. Here's 5 more to bring us up to 10. K1, K2, K3, P1, and P2. And we're going to use those to describe distortion effects. So to account for radial and tangential distortion, we use the Brown-Conradi distortion model. So here it is. Let's say you've got a point xi prime, yi prime. This is a distorted point. Well, that's going to be a undistorted point multiplied by a polynomial, which looks like this. 1 plus k1 ri squared plus k2 ri to the 4th plus k3 ri to the 6th, where ri is just the square root of xi squared and yi squared. So you can think of ri is distance from the center of the image. All right, so if k1, k2, k3 are positive numbers, then you're saying to go from your initial point to your future point, you're going to scale by some positive number multiplied by your distance from the center of the image. That means that in order to describe the true image, you're moving points away from the center. That's pincushion distortion. Or if, for example, k1 is a negative value, now you're saying, okay, well, I know that this point is supposed to be here, but drag it in a little bit, right? Because you're saying, well, it's going to be whatever it was minus some number times its position squared. That's the idea. So negative k1 drags it in, barrel, positive k1 drags it out, pincushion. K1 is the dominant of the radial distortion terms. K2 and K3 are kind of the higher order terms, which have more of an effect around the edge of the field of view. But we're not done yet. What about tangential distortion? So we're also going to say this is 2p1 xi yi plus p2 ri squared plus 2xi squared. And 2p2 xi yi plus p1 ri squared plus 2yi squared. So this is the radial distortion term. This is the tangential distortion term. So P1 is associated with X, P2 is associated, or sorry, P2 associated with X, P1 with Y in this case. And then this is our true point or predicted or pinhole point. And this is our distorted point. As a matter of fact, I'm going to be careful. Maybe I won't say this is the true point. This is the pinhole point. Because actually the distorted point is what you really see in the image. So it'd be more accurate to say that the distorted point is true. Okay. And so our distortion parameters, we use 5 parameters to capture distortion or to describe distortion. K1, K2, K3, P1, and P2. These are radial, and these are tangential. Okay. Now, what if we wanted to undistort our points? So we've got xi prime, yi prime as functions of xi and yi. So I'm saying if I know where a point should be according to the pinhole camera model, and I use the Brown-Conradi distortion model, then I can say, well, here's where you'll find it in your actual image. But the thing is, what I would much rather do is go from the point in the actual image to where it should be according to the pinhole camera model. So we want to be able to work backwards. So what if we're starting with an image? And want to undistort points. Well, a quick glance at this equation, you're not going to be able to solve this backwards, right? Xi and yi are buried in there all over the place. You are not going to get a closed form solution for a Brown-Conradi undistortion. A little bit like when we're talking about Kepler's equation, all the way back in our orbital mechanics discussion. Kepler's equation solves really nicely one way, and the other way you're forced to use some sort of a numerical solution. So we need an iterative solution. So here's the iterative solution. We're going to start with xi initial is xi prime. Yi initial is yi prime. And then, as always, ri squared is xi squared plus yi squared. Okay, so here's the way to think about it. The new xi is xi prime minus 2p1 xi yi plus p2 ri squared plus 2xi squared. And we divide all of this by 1 plus k1 ri squared plus k2 ri to the 4th plus k3 ri to the 6th. And then similarly, yi is yi prime minus 2p2 xi yi plus p1 ri squared plus 2yi squared. Oh, this should be double close. And then divide this by the same denominator. 1 plus k1 ri squared, k2 ri to the 4th, k3 ri to the 6th. All right, so we start by assuming that the distorted points and the true points are co-located, and then we just run this iteration. So iterate till convergence, which is generally less than 5 iterations. So the MATLAB camera calibration toolbox will just do 5 iterations generally. Okay, great. So let's zoom out for a little bit. And I think actually, I'm going to freestyle for a second. I'm going to skip ahead and just looking at my notes. Yeah, we definitely don't have time to go through everything today. So I'm going to talk about one or two more quick little things, and then we'll stop. And then I'm going to push the actual image processing and pixel manipulation to the beginning of next lecture. I think that's going to make the most sense. So I think now is actually a great spot to skip ahead to what was going to be one of my last diagrams. I think this makes more sense here. Okay. So I want to summarize because we just went over a lot of stuff. So I want to talk about the forward and reverse mapping problems. And this is not actually new content. I'm just summarizing what we've talked about. So forward mapping is going to look like this. If you have a point in 3D space, can you tell me what pixel is going to lie on an image? So we start with big XI, big YI, big CI. This is a 3D point. Okay. And then we scale it to get XI and YI. So this is an image plane point. Okay. Then we would distort. To get a realistic image plane point. Or XI prime, YI prime. And then finally, we would multiply by K, the camera intrinsic matrix, or the camera calibration matrix, to get UI and VI, or pixel coordinates. This is the forward mapping problem. The thing is, we generally don't spend our time predicting what pixel is going to be lit up. We generally start with a lit pixel and work backwards to get a direction in 3D space. So that is the reverse mapping problem. So we'll start with another 4 squares here. All right. So in this case, we're going to say standby. I just found a mistake in my notes. Yeah. All right. So if we start with UI and VI, let's say we did our image processing, which we'll talk about next class. We found a bright point in an image. We think it's a star. So we're starting with pixel coordinates. Then we would multiply by K inverse to get XI prime and YI prime. Remember, what you get from your image processing is a real or observed image plane point. But what we want is to undistort to get XI, YI, which is our ideal image plane point. This is the point that the star would light up if this camera had no distortion. So we take account for our distortion here, and then we scale again, or in this case, we're going to normalize, which is a type of scaling. Normalize XI and YI to get EI in the camera frame, or a camera frame unit vector. So the reverse mapping problem is what image-based navigators mostly face. You'll do this on homework 4. And finally, quick aside, this should take 5 minutes and then we'll wrap up. A word on camera calibration. Okay. I want to kind of demystify camera calibration. People are often confused by this. So imagine you have unit vectors in 3D. You've got intrinsic and distortion parameters. And you've got pixel coordinates. Did you notice how you need your intrinsic and your distortion parameters to do the forward or the reverse mapping problem? So let me draw it this way. We're going to do forward as red. So if you know your camera parameters and your unit directions in 3D space, you can get pixel coordinates. But you could also work that backwards. I'll go to blue here. You could say, okay, if I know my intrinsic and distortion parameters and my pixel coordinates, I can solve the reverse mapping problem. This is the reverse mapping problem. But what if you don't know your intrinsic and distortion parameters? And this is a third problem called camera calibration. This is cal. So calibration is just the third math problem after intrinsic and distortion parameters. So forward and reverse mapping and camera calibration form complementary problems. The thing is, if we know, and I'll leave out the details for now, you could use a checkerboard, you could use a synthetic star field image that you cooked up. If you know pixel coordinates and corresponding 3D directions, you can guess and check intrinsic and distortion parameters to best explain the mapping. This would look like this. Perform forward mapping problem. Predict pixel coordinates. Look at error. And what we would basically do is minimize the sum of squared error. So you can take this problem, you can say, okay, look, here's a whole bunch of directions in 3D space. Let me solve and say, if I know my camera parameters, here's where they would be in the image. Oh, but they're not. They're close, but they're not. Okay, let me go back and tweak dx. Does that make it better? Nope, it's worse. Okay, let me tweak it the other way. And you end up with basically a gradient descent problem where you're trying to optimize 10 numbers, dx, dy, alpha, up, vp, k1, k2, k3, p1, p2. You're trying to minimize the sum of your squared residuals. And you can come up with a pretty good initial guess. And I'll do this, and this will be our last point for today. Initial guess of parameters like this. It's reasonable to assume that your distortion is small. K2, K3, K1, P1, P2, and for that matter, alpha, your detector skew, are 0. As an initial guess, distortion is small, detector skew is small. As an initial guess, your principal point is just at the center of the image, which works out to be the number of columns in the image plus 1/2. And VP works out to be the number of rows in the image plus 1/2. It's also reasonable to assume that dy is equal to dx, right? Square pixels. So the only hard one is dx. And dx is going to be the number of columns in the image divided by 2 times the tangent of your field of view over 2. This might seem kind of arcane, but bear with me here. Let's say that you're looking at your image where this is your field of view. This is your focal point at the bottom. And then this is the width of the image. So this is number of columns. This distance is dx. So you can just solve for your trig. Solve some trigonometry to find dx. This is what you'll get. Dx is the number of columns in the image over 2 times the tangent of the half field of view, the half angle of the field of view. Now, to be clear, this is not the answer. This is your initial guess. This will get you pretty close if you have no better idea, if you're really not sure what else to do. If you know the size of your image, n rows and n calls, and you know your field of view in pixels, good enough to start. And then you would iterate on this initial guess. Or you could say, I already calibrated this camera last Thursday. Let me use the results from last Thursday, and then we'll clean them up using this gradient descent method. That's the idea. So you will not be expected to do camera calibration in this class, but there will be a homework assignment in the future where I ask you to solve a navigation problem and I don't give you camera parameters. This initial guess is a great place to start, but that doesn't come up until homework 6. And with that, that was a lot. This went on for longer than I meant it to. We're going to talk about the image processing at the beginning of next class. But let me pause here. Any questions about today's material, or is this enough for now? All right, works for me. I will stick around in case anybody has any questions about specific stuff or homework help or what have you. But otherwise, yeah, great work, everybody. Thanks for hanging in there, and I'll see you on Thursday.